Welcome to today's lecture. Our topic is Classical NLP Foundations and Modern Text Pre-Processing. In this lecture, we will build a strong baseline for text classification using TF-IDF, and we will evaluate it in a leakage-safe way. Here is the big picture. We are not trying to use the most advanced model today. Instead, we want a baseline that is fast, interpretable, and reliable. Next week, when we move to embeddings and transformer-based models, we will compare their performance against this baseline. By the end of today's lecture, you will be able to do three things. First, you will define a core text cleaning policy that standardizes noisy marketing text. Second, you will build a TF-IDF baseline with a linear classifier. Third, you will evaluate the model without data leakage by fitting pre-processing steps only on the training data using pipelines. Here is today's agenda. We will start with core cleaning and quick sanity checks. Then we will build our baselines, comparing count features to TF-IDF. After that, we will add n-grams to capture short phrase signals. Next, we will interpret the model by inspecting the top positive and negative terms. Then we will run a leakage demo to compare a wrong evaluation pattern to the correct one. Finally, we will summarize what we need as a reference point for next week. Now let's begin by loading a small streaming sample from the Yelp Polarity dataset. In this part of today's lecture, we are going to load a small sample of real review text data. To keep things lightweight, we will use the Hugging Face datasets library in streaming mode. This lets us iterate through the dataset without downloading the full dataset up front. I am also installing TQDM so we can see a progress bar while sampling. Next, I import the libraries we will use throughout the lecture, including NumPy, Pandas, and scikit-learn. Finally, I set a fixed random seed. This is for reproducibility, meaning you and I should see similar results when we run the same steps. Now we will load the Yelp Polarity dataset using streaming mode. Streaming returns an iterable dataset, so examples are produced as we iterate rather than being fully downloaded and stored first. For today's lecture, we only need a small subset for fast experimentation. I will sample 3,000 training examples and 1,000 test examples. Because streaming data cannot be perfectly shuffled without loading everything, we use an approximate shuffle. This shuffle uses a finite buffer, and it randomizes within that buffer. A larger buffer produces better randomization, but it uses more memory and can be slower. Next, we define a small helper function called takeN. It iterates through the stream and collects exactly n examples. We wrap the loop with a TQDM progress bar so you can see that sampling is actually moving forward. After sampling, we convert the sampled rows into Pandas data frames. Then, we validate that the dataset has the expected columns, text, and label. Finally, we prepare X and Y for modeling, with X as the review text and Y as the binary sentiment label. At the end of this cell, we print the shapes and the label distribution for train and test. Ideally, we should see reasonably balanced classes, and train and test should look consistent. Before we build any models, we do a quick sanity check. There are three things to verify. First, check the label distribution. If one class dominates, accuracy can be misleading, so we rely more on metrics like AUC and F1. Second, check typical text lengths. If documents are unusually short or unusually long, that affects sparsity and how we choose vectorizer settings. Third, print a few examples. This confirms that the text content and labels look reasonable for sentiment polarity classification. Now I will inspect the dataset more directly. First, I print the raw label counts for train and test. This is just a quick confirmation that class balance is reasonable. Next, I compute length summaries in two ways. I summarize character lengths, and I also summarize approximate word counts by splitting on whitespace. This is not a perfect tokenizer, but it is a fast way to understand the scale of the text. Finally, I display a few random examples from the training set and the test set. I collapse whitespace so the previews are readable, and I truncate long reviews to keep the output compact. At this point, we have a clean, reproducible setup. We have text inputs, labels, and a quick understanding of what the data looks like. Now we are ready to move to core cleaning. In this part, we define our core cleaning policy. Core cleaning means a small set of rules that make text consistent, reduce noise, and preserve signal. First, we normalize and standardize the text. This means we make formatting consistent across examples, especially in coding and whitespace. Second, we replace certain patterns instead of deleting them. For example, when a review contains a web link, we replace it with a URL placeholder token. When a review contains a user mention, we replace it with a user placeholder token. This removes messy, unique strings while still preserving the information that a link or a mention existed. Third, we keep meaningful tokens when they may matter. In marketing text, numbers, product models, and brand names can be predictive, so we avoid aggressive deletion that could remove useful signal. Now that the policy is clear, we will implement it as a reusable cleaning function and apply it to both training and test text. Let's define a function called cleanText. This function applies our core cleaning policy in a consistent way. The key steps are Unicode normalization, HTML removal, URL replacement, user mention replacement, and whitespace cleanup. We also precompile the regular expressions. That makes the code cleaner and slightly faster, especially when we run it across thousands of reviews. Once this function is defined, we can apply it to any text column using the same rules, which is important for reproducibility. Now we apply the cleaning function to the training text and the test text. Then I print a small set of examples, showing the original text and the cleaned text side by side. When you look at these examples, focus on three things. First, the text should become easier to read with cleaner spacing. Second, HTML artifacts should disappear. Third, links and user mentions should be replaced with stable placeholder tokens, not removed in a way that changes the structure too much. This is a quick qualitative check to make sure our cleaning rules behave as intended. Next, we compute simple sanity metrics after cleaning. These are not modeling features. They are quick diagnostics to make sure we did not accidentally damage the data. We summarize typical text length in characters and in approximate word counts. We also compute how often a URL placeholder token appears and how often a user placeholder token appears. Finally, we print the most common tokens using a very simple tokenization approach just for a quick overview. When you review these outputs, look for anything surprising. If the average length drops dramatically, a rule may be deleting too much. If the placeholder token rates look unrealistic, the replacement patterns may be too broad or too narrow. And if the top tokens look strange, that can reveal unexpected formatting issues. At this point, we have a standardized text input that is ready for classical feature extraction. Now we move to classical baselines using sparse text features. In classical text modeling, we represent each document as a high-dimensional vector. Most entries in that vector are 0 because each document uses only a small fraction of the full vocabulary. That is why we call these representations sparse. We will start with a count-based representation, often called bag-of-words. Here, each feature is simply how many times a token appears in the document. Then we will use TF-IDF. TF-IDF reduces the influence of very common words and highlights more informative terms. In many practical settings, TF-IDF is a strong default baseline. These baselines matter because they are fast, interpretable, and surprisingly competitive. They also give us a trustworthy reference point for comparing embeddings and transformer-based models later. Now we set up evaluation for our baselines. We keep evaluation simple and consistent. We already have a train and test split from our streaming sample, so we will train on the training set and evaluate on the test set. We will report two metrics. First is AUC, which measures how well the model ranks positive examples above negative examples across all thresholds. Second is F1 score, which balances precision and recall at a specific decision threshold. Using a small number of clear metrics helps us focus on the modeling choices rather than getting lost in many performance numbers. Now we build our first baseline model. We use a count-based vectorizer and logistic regression. The important detail is that we put everything into a single pipeline. This ensures that the vectorizer is fit only on the training data and then applied to the test data in a consistent way. After training, we evaluate on the test set and print AUC, F1, and accuracy. This gives us a simple and interpretable first benchmark. Next, we build a second baseline that uses TF-IDF instead of raw counts. The model remains logistic regression and the pipeline structure stays the same. So the only change is the representation. After fitting the pipeline on the training data, we evaluate on the test data and print the same metrics. Then we print a one-line summary showing the difference between TF-IDF and the count baseline. This makes it easy to see whether TF-IDF improves ranking performance and overall classification quality. Now we introduce a few practical settings that control the vocabulary. First is minimum document frequency. This removes tokens that appear in only a small number of documents, which often behave like noise. Second is maximum document frequency. This removes tokens that appear in almost every document, which often carry little information. Third is the maximum number of features. This caps the vocabulary size, which can reduce overfitting and make training more efficient. We will try a small number of controlled settings and compare both the number of features and model performance. Now we run a controlled comparison across a few TF-IDF configurations. For each setting, we train the same model and evaluate it the same way. We also record the number of features because feature size affects both overfitting and computational cost. At the end, we display a small table that summarizes each setting, the feature count, training time, and performance metrics. This helps us choose a practical TF-IDF baseline to carry forward. Now we move to n-grams, which help us capture short phrase signals. A unigram is a single token, basically one word at a time. A bigram is a sequence of two consecutive tokens, a two-word phrase. Why does this matter? In sentiment tasks, meaning often comes from short phrases. For example, the phrase "not good" carries a different meaning than the word "good" by itself. Bigrams help the model represent that phrase directly. There is one practical warning. When we add bigrams, the number of possible features can grow quickly. This is called feature explosion. To keep the model stable, we combine n-grams with vocabulary controls such as minimum document frequency and a maximum feature cap. Now we will compare unigram only TF-IDF versus unigram plus bigram TF-IDF, and we will look at both performance and feature size. Let's run a controlled experiment. Both models use the same classifier, logistic regression. The only difference is the n-gram range used by the TF-IDF vectorizer. First, I train a unigram-only model. Then I train a model that includes both unigrams and bigrams. For each setting, I record three things: the number of features, the training time, and the evaluation metrics on the test set. At the end, you will see a small comparison table. When you read the table, focus on the trade-off. The uni plus bigram model usually increases the feature count substantially. That can increase training time and memory use, but it may improve performance because it captures phrase-level sentiment cues. Finally, I print a one-line summary showing the change in AUC and the change in F1 when moving from unigrams to unigrams plus bigrams. This makes it easy to decide whether the extra complexity is worth it for this dataset. Now we move to interpretability. Because we are using TF-IDF features and a linear model, we can inspect term-level influence. The model learns a coefficient or weight for each token feature. A positive coefficient pushes predictions toward the positive class. A negative coefficient pushes predictions toward the negative class. This is useful in marketing settings because it gives us a transparent view of what language is associated with positive versus negative outcomes. Now let's extract the most influential terms from the trained pipeline. I take the fitted vectorizer to get the feature names, and I take the fitted logistic regression model to get the coefficients. Then I sort terms by coefficient value. First, I display the top positive terms, the ones with the largest positive coefficients. These are the terms that most strongly increase the probability of the positive class. Next, I display the top negative terms, the ones with the most negative coefficients. These terms push predictions toward the negative class. As you look at these lists, focus on whether the terms make intuitive sense for sentiment. Also, pay attention to any surprising tokens that might reflect data quirks or pre-processing artifacts. This interpretability snapshot is part of what we will carry forward as our baseline reference for next week. Now we move to the core demo on leakage-safe evaluation. Data leakage happens when information from the test set influences any part of training. In text modeling, the most common leakage is fitting the vectorizer using all texts, both training and test. Here's the key idea. A vectorizer is not just a simple converter. When we fit a TF-IDF vectorizer, it learns a vocabulary and it learns global statistics such as inverse document frequency weights. Fit means learning those statistics from data. Transform means applying the learned mapping to new data. So if we fit TF-IDF on training and test together, the test set shapes the feature representation. That makes evaluation less credible and it often inflates performance. In this section, we will compare two patterns. First, the wrong pattern where TF-IDF is fit on the full dataset. Second, the right pattern where TF-IDF is fit only on the training set and then applied to the test set. In practice, the easiest way to enforce the right pattern is to use a pipeline. Now I will demonstrate the wrong approach. I first combine the training text and the test text into one large text collection. Then I fit the TF-IDF vectorizer on that combined text. This step is exactly where leakage occurs because the test data influences the vocabulary and the IDF weights. After that, I transform the text into features, and only then I split the feature matrix back into training and test portions. I train logistic regression on the training portion and evaluate on the test portion. When the metrics appear, notice that they may look unusually strong. This is inflated performance, and we cannot trust it as a fair estimate of generalization. Now I will run the correct approach. Here we use a pipeline that contains TF-IDF vectorization and logistic regression. The pipeline is fit only on the training data. That means the vocabulary and IDF statistics are learned only from training text. Then, the same fitted pipeline transforms the test text and produces predictions for evaluation. This is leakage safe, and this is the pattern you should use in your own work. When the metrics appear, compare them to the wrong approach. This result is typically lower, but it is more credible. Now I summarize the difference between the wrong and right evaluation patterns. First, I show a small table with AUC, F1, and accuracy for both methods. Then I compute the inflation caused by leakage, reported as the difference in AUC and the difference in F1. The key takeaway is simple. If you allow the vectorizer to learn from the test set, performance is overstated. Using a pipeline prevents this mistake and gives you an evaluation you can trust. Now we wrap up today's lecture by summarizing what we will carry forward to next week. The main goal today was to build a reliable reference point. Next week, when we move to embeddings and transformer-based models, we will compare them against this baseline. Here is what we are carrying forward. First, the model configuration. This includes the representation we used, such as TF-IDF, and the classifier, such as logistic regression, along with key settings. Second, the core cleaning policy. We standardize text in a consistent way, removing obvious noise and replacing patterns like links and user mentions with stable placeholder tokens. Third, the performance metrics. We report a small set of metrics such as AUC and F1, evaluated on the same split using a leakage-safe pipeline. Fourth, an interpretability snapshot. We keep the top positive and top negative terms and their weights, so we can understand what language is associated with positive and negative outcomes. Keeping this baseline makes it easy to answer a simple question next week. How much do embeddings improve performance, and how does interpretability change? That completes today's lecture.